Namaskar everyone. A very good afternoon and a very warm welcome to one and all. Our distinguished guests, my colleagues, my dear students, ladies and gentlemen, and all the esteemed participants of this webinar. One of the most defining characteristic of Indian culture is hospitality or welcoming nature. In our country, we have the highest regard for our guests and value the hospitality the most, be it in on any occasion or the platform. A common saying here is Atithi Devo Bhava, meaning guests are the form of a god. Having said that, on behalf of University of Petroleum and Energy Studies, UPES Dehradun, and my own behalf, I extend a warm welcome to our distinguished guest for today, industry expert and the speaker, Padma Vibhshan, Dr. G.Madhavan Nair, former chairman, Indian Space Research Organization, ISRO, Government of India. We would have to welcome you in person at our university, and it would have been a privilege for us to have you here, sir. Nevertheless, it is still a matter of great pride and privilege for us to welcome you on this platform and listen your key insights on the topic rocket technology and future prospects of avionics engineering. Ladies and gentlemen, my name is Dr. Sudhir Kumar Chaturvedi, faculty in the Department of Aerospace Engineering, University of Petroleum and Energy Studies, UPES Dehradun. I would like to quote three Sanskrit words, Adhigachati Janati Gyata. It means learn, learn, and learn. And UPES follows the line, learning never stops. A very important shloka in the Sanskrit correlates to the space engineering, space technology, avionics technology. Om Go Shanti Antariksha Shanti Prithvi Shanti Rapah Shanti Ro Shadayah Shanti Vanaspatayah Shanti Shanti Vishudeva Shanti Brahma Shanti Sarvashanta Shanti Shanti Reva Shanti Shama Shanti Redi Om Shanti Shanti Shanti. It means Om. Peace is in the sky, peace is in the space, peace is in the earth, peace is in the water, peace is in the plants, peace is in the trees, peace is in the gods, peace is in the Brahma, peace is pervading to everywhere. Peace alone is a peace, and may you be that peace makes our life peaceful. Om Shanti, Shanti, and Shanti. UPES envisions itself as an institution of global standing, which fosters developing the professionally competent talent and contributes to the nation building. With such a vision in our mind, we had taken another leap in this journey, where we had started a webinar series that gives us a chance to interact with and hear from the industry some of the most prominent and renowned personalities of all time. To add another feather to this hat, we have come up with another interesting webinar for the today's topic, rocket technology and the future scope of avionics engineering. We at UPES Dehradun in India are delighted and honored to host today's webinar in the auspicious presence of Padma Vibhushan Dr. G.Madhavan Nair, former chairman, ISRO. Before introducing the chief guest, I would like to give a brief about the avionics. Avionics refers to the electrical equipment used in missile, aircraft, spacecraft. Aviation electronics are the navigation, weather radar, and radio communication equipment used by pilots. This industry developed with the rise of modern warfare and hundreds of advancement and developments since World War II. Avionics engineers work in the aerospace industries, designing and developing aircraft, spacecraft, satellites, missions, and spacecraft avionics instrumentation. You would be researching problems associated with flight safety system, landing gear, and electronic navigation systems. Additionally, you would test the prototype to make sure that they function according to the design. Avionics engineers often specializes in designing the aerospace products. These products can be civilian or military airplanes and helicopters, remotely piloted aircraft and rotorcraft, spacecraft such as launch vehicles, satellites, military missiles, as well as the rockets. Avionics engineers have many duties and responsibilities to help installing and serving the avionics components, equipment, and making sure that these systems completely work with the design or not. You actively design, purchase, test, and calibrate the computer and electronic communication panels. We at UPES Dehradun offers the program in BTech Aerospace Engineering with their specializations in avionics. You know and aware the various avionics tools and technologies within our country and globe. Without avionics, there is no use of making or designing the vehicles. Avionics is the useful for controlling, monitoring, and the spacecraft, aircrafts, as well as the satellites. Now it's time to introduce our today's guest, Padma Vibhshan, Dr. G.Madhavan Nair. Dr. G.Madhavan Nair, the former chairman of Indian Space Research Organization, ISRO, former president of International Academy of Astronautics, Paris, former chairman of Center for Management Development, Government of Kerala. He held various posts such as Secretary to the Government of India, Chairman, Board of Governors, IIT Patna, and was council member of Indian Institute of Sciences, Bangalore. Born in Neyatatikara, Thiruvananthapuram, Kerala on October 31st, 1943. Dr. G.Madhavan Nair graduated in engineering from Kerala University in 1966 and after training in Bhabha Atomic Research Center, Park, Mumbai, joined Thumba Equatorial Rocket Launching Station, TERLS, in 1967. He is one of the pioneers who had the opportunity to work with the founding father of ISRO, Dr. Vikram Sarabhai. During his tenure of more than 4 decades in ISRO, he had made significant contribution to the Indian space program. He is also known as the architect of Indian space rocketry and avionics program. Dr. G. Madhavan Nair joined Thumba Equatorial Rocket Launching Station in 1967. Since then, he held various positions illustrating milestones on his way to the position of chairman ISRO. 1967 to 1972, he was the head of Payload Integration Section, PERS RLS Trivandrum. 1972 to 74, he was the project manager in Telecommand System VSSC Trivandrum. 1974 to 80, he was the project engineer of SLV3 project Trivandrum. 80 to 84, he was the head of Electronic Systems VSSC Trivandrum. 1984 to 88, he was the project director of PSLV in Trivandrum. 88 to 95, he was the project director of Polar Satellite Launch Vehicle PSLV in Trivandrum. 1994 to 96, he was the program director for ILVP VSSC Trivandrum. 95 to 99, he was the director of Liquid Propulsion System Center Trivandrum. 99 to 2003, he was the director of Vikram Sarabhai Space Center Trivandrum. 2003 to 2009, he was the chairman of Indian Space Research Organization Bangalore. 2010 to 2015, he held various key positions such as he was the president of International Academy of Astronautics. Welcome, sir. Welcome you to the UPES. Now, furthermore, as a chairman of ISRO, he had given a new vision to the Indian space program and directed the development of space technology. He was responsible for implementing India's first mission to Moon Chandrayaan-1, which provided a unique opportunity to the scientific community to study the surface features of the moon, its mineralogy, and ultimately the leading to the confirmation to presence of water on the moon. He has given a significant thrust in implementing the application programs such as the education, telemedicine, and disaster management support systems for the meeting needs to the society at large. A scheme for the village resource centers through the satellite connectivity is implemented, providing multiple services in a single window, which aims in improving the quality of life of the poor people in the villages. During his tenure as a 6th year as a chairman ISRO as well as the secretary to the Department of Space Government of India, 25 successful missions got accomplished, such as INSAT 3E, ResourceSat 1, EduSat, Cartosat 1, HAMSat 1, INSAT 4A, PSLV C5, GSLV F1, PSLV C6, Cartosat 2, INSAT 4B, SRE1, PSLV C7, PSLV C5, GSLV F04, INSAT 4CR, PSLV C10, Cartosat 2A, IMS1, PSLV C9, Chandrayaan 1, PSLV C11, PSLV I2, PSLV C4, and OceanSat 2. He has taken initiatives towards the development of futuristic technologies to enhance the space systems capabilities and reduce the cost to access the space. He has given a significant thrust for evolving the application programs such as teleeducation, telemedicine for meeting the needs to the society at large. As of today, more than 31,000 classrooms have been connected under the EduSat network, and telemedicine is extended to 315 hospitals, 269 in remote and rural hospitals, including 10 mobile units in the 46 specialty hospitals. He has initiated scheme of the village resource centers, VRCs, through satellite connectivity which aims to improve the quality of life for the poor people in the villages as well as the remote areas. More than 430 VRCs facilitates access to the spatial information on the essential aspects such as the land use, land cover, soil and groundwater prospects to enable the farmers to make the critical decision based on their queries. VRCs also enables the online interaction between the local farmers and agriculture scientists. It also provides the information on many governmental schemes, farming systems, action plans based on weather community services, advice to the soil and water conservation, etc. In his tenure as a liquid propulsion system centers director in 1995 to 1999, India's efforts toward the indigenous development of cryogenic technology took concrete shape and vital infrastructures were built and critical technologies were developed. In his role as a director of Vikram Sarabhai Space Center in 1999, till he took over the position of a chairman, largest India center as a ISRO, which for, with about 6,000 employees working in a various engineering and scientific disciplines towards the development of India's geostationary satellite launch vehicle (GSLV), which is capable of orbiting 2,000 kg class of satellites into the geotransfer orbit, which had its successful flight in its very first attempt and declared operational after its successful flight in year 2003. He was also responsible for charting and roadmap for the future development of ISRO's activities, especially in the launch vehicle area targeting the low-cost access to the space. Dr. G.Madhavan Nair has led the Indian delegation to the Science and Technology Subcommittee to United Nations Committee on Peaceful Uses of Outer Space since year 1998. Dr. Madhavan Nair's has always been to, to achieve the self-reliance in the high technology area and bring the benefit of the space technology to the nation developments, especially targeting the needs for the rural and poor section of the society. Dr. Nair is a specialist in rocket sciences and has made a significant contribution in the development of satellite launch vehicles such as SLV-3 to the GSLV. He was the chief architect of India's workhorse launcher PSLV. He had initiated several new missions such as semi-cryogenic engines, recoverable and reusable launch vehicles, Indian Regional Navigation System, and human crewed missions. He was instrumental in establishing the Indian Institute of Space Sciences and Technology, Thiruvananthapuram. Dr. Nair has been bestowed with the several awards such as National Aeronautical Award, Fellow of Institution of Engineers Foundations Award, Shri Om Prakash Bhashin Award, Swadeshi Shastra Puraskar Award, Vikram Sarabhai Memorial Gold Medal of the Indian Science Congress Association. He is the recipient of Gold Medal from Prime Minister at 94th Indian Science Congress in year 2007. Our country, the nation has honored him by conferring Padma Bhushan in 1998 and Padma Vibhshan in year 2009. Dr. Madhavan Nair has been conferred with the Doctoral of Science, Doctoral of Philosophy from 19 different universities and IITs such as Punjab Technical University, Sri Venkateshwara University, IIT Delhi, Indira Gandhi National Open University, Cochin University of Science and Technology, University of Mysore, Rajiv Gandhi Technological University Bhopal, University of Kerala, Karnataka University, IIT Bombay, and IIT Kharagpur, as well as the Northeastern University Shillong. Dr. Madhavan Nair is a Fellow of Indian National Academy of Engineering, Fellow of the Astronautical Society of India, Fellow of the National Academy of Sciences India, Honorary Fellow of Indian Society of Non-Destruction Testing, Member of the System Society of India, Member of the Working Committee of the Current Science Association, Member of the International Academy of Astronautics, Senior Associate of National Institute of Advanced Studies, President of Inter-Sputnik Board, Honorary Fellow of the Aeronautical Society of India, Honorary Life Fellow of Institution of Engineers, former Chairman of Research Council of National Aerospace Laboratory, and the former President of International Academy of Astronautics. His passion is popularizing science among the school children and finding the solutions to the common man's problem through the application of science and technology. His wife is Srimati Radha Kumari, an ISRO scientist, and they are staying in Thiruvananthapuram. They have the two sons, Dilipan and Jai Krishna, and grandchildren as Aditya and Narayana. Thank you once again, sir, for accepting our invitation to deliver this talk. Welcome to University of Petroleum and Energy Studies, UPES Dehradun. Most welcome, sir. Now it's over to you to give us the brief insight of rocket technology and the future prospects of avionics engineering. Thank you, sir. Thank you so much. It's over to you.
Thank you, Professor Sudhir Kumar, for the elaborate introduction as well as a warm welcome which you have extended. Uh, well, it's my pleasure to address the distinguished faculty members and students who are participating in this webinar. I have visited your institute maybe about 11 years back, 2009, and I have fond memories of that institution. At the time, it was only just a small one which is emerging, but today I can see that you have grown into a multidisciplinary and global standard institute, which is doing excellent service to all the student community in the country. I know that students from various parts of India are there, and they are, in spite of this tragic time of COVID, your institute is doing justice to the academic activities using the modern technology of computers and smartphones. Now, I think my job has been made simple by Professor Sudhir Kumar. He has highlighted what ISRO has achieved, and to that extent, I don't intend to repeat them. But let me try to just place the record uh, how we started and where we are today. Well, it was in the 60s that the great visionary scientist Dr. Vikram Sarabhai has conceived that India must have its own space program. And he has set the goal that we should be self reliant in the space technology and its application for the benefit of the common man. This is a time frame in which the Sputnik has been just launched, and Americans have the GEM mission to the orbit, the satellite and the human to the orbit. And that's immediately after that is where India has just entered the field. But the events which as Russians or Americans have achieved is a tireless effort starting from World War II. So that way we have a late start, something like 20 years later compared to others. But today we can be proud to say that we are one of the superpowers in space technology. We have a huge rockets which can carry tons of spacecraft into orbit, use the spacecraft for communication connectivity, Earth observation, um, then providing various means of scientific experiments and so on. So that way, we have a totally self-reliant, homegrown technology which is of world class, and we can be proud that all these have been achieved with the tireless efforts of engineers and supporting staff who have come from various institutes in the country. They are all homegrown products. So it is not only the technology which is homegrown, the people who are behind these technical achievements also are homegrown. So that's a very unique situation. There are many countries, even China, they had the support of Soviet Union in starting their space program and so on. But whereas India, we were denied access to this high-tech area right from beginning. In fact, that was a blessing in disguise, and it has helped us to work harder to learn the technology from scratch and perfect it so that we have a series of successful missions year after year. Well, when we started, it was only as a sort of a experiments for sounding the atmosphere using rockets. We send a set of instruments at the head of the rocket, and these instruments reach an altitude of nearly 100 to 150 kilometers. And during its ascent as well as descent, which is lasting about 10 minutes, various parameters of the atmosphere will be collected and telemetered back to the ground. So that was the starting point. And initially, the rockets came from USA, Europe, and Russia. But later, we felt the need for developing these rockets ourselves. You may recall India had a very prestigious past, so to say, when we had used a rocket developed by Tipu Sultan against the British Army in the 18th century. Well, those rockets were a deadly weapon against the British Army, and of course they have conquered the Sultanate and captured all the weapons and technicians and taken to their country. After that, we have not done anything in rocketry until the space program has started. So that is a big gap we had. But whereas in the World War II time, the V2 rocket, which was developed by Germany, became the threatening weapon to the Allied forces. And of course, again, the German army was defeated, and the US as well as Russia captured the scientists, technicians, and the hardware from Germany. And those hardware became the reference for developing missiles for delivery of the atomic weapons by these two nations competing with each other. Whereas we had just only small pencil rockets when we started in the 60s. It is just slightly bigger than the Diwali rockets, what you see today. It can carry uh, the a small payload, let's say about 10 kilogram, to an altitude of about 10 kilometers. Compared to that, today we have the GSLV Mark III, which is the most powerful rocket system which the country has. It can carry a 10-ton capsule to an altitude of nearly 600 kilometers and place it around an orbit in the near Earth zone. So this is a fantastic achievement, I would say. And again, this GSLV Mark III is going to be man-rated so that the human beings can be flying in the manned capsule to space and safely return to ground. So that's a kind of phenomenal growth what we have achieved during these days. When you talk about the rockets, basically it has to have a propellant which is carried on board, and then a nozzle system through which the hot gas is expelled, by which the thrust is generated, and so on. But to keep its course corrected, one should have a control mechanism. So quite often, the rocket engine itself is fuel placed in gimballs, and it is turned using hydraulic actuators in the pitch and yaw direction to get the controls. But in the solid motors, this type of system is rather difficult. So initially, they developed a system by which the liquid under high pressure is injected into the nozzle, by which the thrust can be deflected. I'm just referring to the control system so that you will get the relevance of this with respect to the avionics, which I come back to later. Now, these rockets, of course, when you're making the pencil rocket itself, Dr. Sarabhai has given us a goal, challenging goal, that we must be able to launch a satellite, at least about 40 kilogram satellite, into near Earth orbit. This was equivalent to what is called a Scout launch system, which US had, and they have used for various scientific exploration at the time. In fact, no wonder, due to the technical commitment, the hard-working nature, and the leadership characteristics, this project was given to Dr. APJ Abdul Kalam. And I had the opportunity to work in the team right from the beginning. And in 1980, we had the first successful launch of SLV-3, in which we carried a 40 kilogram satellite into the low Earth orbit. Well, of course, the first launch of SLV-3 was a failure, that again due to a control system malfunctioning. But later, there was a need was felt to enhance it to something like 500 kilogram at least. That is where the Polar Satellite Launch Vehicle concept came in. Here, it is not only a solid rocket, which was nearly 20 times larger than what was used in the SLV-3 to be developed, but also liquid propellants, hyperbolic liquid stored in the tanks on board the rocket was used for the first time in the country. The second stage, which was conceived for PSLV, that has become really a workhorse all three these years. It has been used in the PSLV, it is used in the GSLV, later in the GSLV Mark III, and so on. And then subsequently, the need for achieving a geostationary orbit, they became imminent, and we need more efficient system, uh, so better fuel as we use. That is where the use of hydrogen and oxygen as fuel was selected. With this mixture, one could achieve the highest thermal efficiency in chemical propulsion, and we had used that for the first stage of GSLV. Here again, the gas cannot be stored unless under with high pressure on board, and that's not very efficient. You require large mass for containing this gas under high pressure. So we have adopted technology by which this gas is liquefied, and the liquid temperature, as you know, hydrogen about 20 Kelvin and oxygen about 80 Kelvin. At those temperatures, cryogenic temperatures, this has to work. That's how the name cryogenic rocket came in. Yes, in the initial stages, we had some tie-up with Russia. They were willing to give us the technology for the cryogenic stage. But when the USSR broke up, because of the political pressures and other thing, they withdrew from this contract, and we were forced to do it ourselves. Yes, we didn't look back. We have developed that technology as well. So we have a series of propulsion elements which forms modules which can be configured for the polar satellite launch vehicle, geostationary launch vehicle, the satellite propulsion, the mission to moon, mission to Mars, etc. But the PSLV, which I had the fortune to lead the team, we have developed in the 80s, and in the 94 we had a first successful launch with about near 800 kilogram. Today that has been optimized, and the same PSLV is able to carry something like 1,500 kilogram into the Earth orbit. The same, this PSLV is what is used for the Chandrayaan 1 mission, the first mission to moon, and also for some of the small geostationary satellite launches. Now, once we have this rocket system, then comes the role of avionics. Let me briefly touch upon that. Of course, initial period, we were doing the sounding of atmosphere. Here, the basic requirement is to have the sensors which will acquire the data about the atmospheric wind, pressure, temperature, humidity, and so on. So these sensors output will be very low level signals. They have to be suitably conditioned to high level, as well as using appropriate filters. Their bandwidth has to be limited, and thus it can be used through the telemetry. The telemetry is nothing but a transmit receive system. The transmitter is in the rocket, and the receiving setup is on the ground. As the rocket flies, without any physical connection, through this RF link, we can have the data transmitted and then received on the ground, deciphered for various scientific analysis and so on. Of course, in the initial stages, we try to use the conventional frequency modulation technique, but later, when more large volume of data has to be handled, we had to adopt to the digital data transmission. This I'm talking about in 70s. In 1970s, there was no digital communication in the country, but ISRO scientists and engineers made the encoders for digital transmission and decoders on the ground for receiving and deciphering this data and interfacing with the computer and so on. So that was the beginning of the avionics system for the space program. But that is for the simple sounding rockets for collecting scientific data. But when it comes to controlling a vehicle like SLV-3, PSLV, or GSLV, and taking it precisely to an orbit, we require a lot more. That is where the avionics systems really saw its golden era in the country. Of course, other countries like France or Russia, Russia was not that advanced, but USA, they had very advanced technologies for these. And but unfortunately, since it is being of a dual use nature, they will not share the technology with us because the missiles also use a similar system. The first and foremost is what is called inertial navigation unit. The rocket lifts off from the launch pad and then travel to space, normally, typically a distance of nearly 600 kilometers in altitude and range-wise a few thousand kilometers. This distance, when it is covering, we must be able to locate it precisely using the onboard instrumentation. The first and foremost is the acceleration. Three-axis accelerometers are mounted on the rocket, and also the rotation of the rocket about this axis has to be measured. Here, the rate gyroscopes, rate integrating gyroscopes are incorporated. Uh, of course, the principle of a gyroscope is very well known. A spinning wheel, and it maintains its reference, and any disturbance coming at a lateral direction will be converted to torque in the perpendicular direction, and that using appropriate torque sensors, we can measure the rates. It is said simply, but this motor, which is very tiny, it has to work at a speed of nearly 24,000 RPM and continuously for hours together without any degradation. So this has been a big starting point, a big challenge to start with. Then, of course, realizing these rate sensors and trying to have a precision measurement of the rates using inductive sensors, and then converting this to electrical signals and using it for further operation, etc., has been a challenge. Of course, initially we used what is called a inertial platform. Here, the gyros and accelerometers are put in a cluster, and this cluster is suspended in a four gimbal system. That means one can keep the cluster steady in a direction as at the launch pad, even if the rocket turns this way, that way, and travels forward and so on. This is achieved by having closed loop control mechanism of each of the gimbals. That essentially means the rate sensor output is used to on a null seeking mode. There's a servo amplifiers which is used to drive the servo motors, and there are sensors which will pick up the angular rotation of these gimbals and so on. So a series of electromagnetic, electromechanical devices had to be used and combined with analog electronics. That was what was predominantly available at the time. Still, for the SLV3 program, we have achieved a platform which was comparable to the global standards. This type of inertial navigation system was used at the time in even in the civilian passenger aircraft. Its overall performance is measured in terms of the accuracy after a 1 hour of flight. Normally, it was about 1 nautical mile after 1 hour of flight. So that means in a distance of nearly 600 kilometers, 1 nautical mile is what is permissible. But what we could realize was an order of magnitude better than this. Something like 0.1 nautical mile per hour is a specification what we could achieve. But always when you have a large number of moving parts, mechanical system, the motors, and the basic gyroscope itself, which is working on a mechanical element, these are all become reliable concern. So normally the MTBF of the system doesn't exceed more than a few hundred hours. So that means its reliability is also accordingly low, or even for short missions. So this led us to the development of a new concept in which these gyros and accelerometers are mounted directly on the rocket in its axis, and then entire processing of the signal, converting the body axis measurements to inertial axis, is done through digital computers. So this again, we took a risk in the PSLV time frame. We never had a digital computer even for ground processing. There were one or two in the Tata Institute of Fundamental Research and maybe some high institutes of learning. Even for ISRO, there was only a small computer which is available. So that is where ISRO took up the challenge of making an onboard computer. It should have a performance equivalent to conventional PC today, and it has to be packaged within a volume of nearly 30 centimeter cube. So this is has been a very big challenge. Even the basic parts which are required for this were not manufactured in the country, and none of these developed nations will give. So we had to go through the commercial markets in the Gulf countries or in Singapore and pick up off-the-shelf components and screen them, upgrade them, and use it for realizing the computer. That computer did the work for ASLV, then later for the PSLV, and the initial flights of GSLV as well. In the meantime, the Vikram Sarabhai Space Center at Thiruvananthapuram took up the challenge of making a basic computer chip. It is called Vikram computer, which is again, it's not a very high-end one, but with a reasonably good computational speed, a 16-bit machine. It was initially designed here, but since we did not have a foundry in India, we had to take it to France for fabricating. So at one go, we fabricated sufficient number of those chips, and that became the mainstay for subsequent flights of PSLV and GSLV. Even today, that is being used. Later, when the need came for realizing this component in the country, again there is, even today, there are not many fabrication facilities, silicon fabrication facilities in the country. Why not many? There's only one. The Chandigarh, there was a semiconductor complex which was early days, but it got gutted in a fire and damaged, and they were not really advancing. At that time, ISRO took the responsibility of revamping the facility and making it modern with something like 180 micron technology, combining the digital analog circuits and so on. That became the mainstay for making the critical devices for the space program, as well as it needs some other requirements for the missiles too. Well, that's where we have matured from a mechanical system to a digital system for making the inertial measurements. Again, in the sensors, to overcome the reliability problem, we have adopted the concept of laser gyros. You know, the laser beams you put in a loop clockwise and counterclockwise. When there is a body rate around its normal axis, it comes as a phase shift in between these two signals. That is the one which is. This is I would say, it's a perfect solution. In a sense, there is no moving parts, and the type of accuracy which you get in these gyroscopes are 100 times better than what you get in a mechanical system. This again has been developed in inertial systems unit at Thiruvananthapuram, and this is the one which is being flown in all our modern rocket systems. Then came about the control. The vehicle has to be stabilized in three axes. The engine has to be controlled in different direction, and so on. So this initially, again, we were using analog electronics with the power modules driving various motors. But later we thought it is better to go for digital technique. In fact, we were the first to use uh, in the world, I will say, a digital autopilot in ASLV. That was in the early 80s. And later we have perfected this. In all our flights, it is a digital autopilot being used. And perhaps it took another 20 years before the other nations turned towards digital autopilot. And today that is a very common element in almost all the aircrafts. The basic technology which is required for the digital autopilot has been developed. The navigation control. Then comes the guidance. Guidance means you have to, from the starting point to the end point, you have to steer the direction of the rocket in such a way it precisely arrives at the destination. To achieve this, a very sophisticated set of equations has to be solved in real time. Again, we have resorted to digital techniques. Digital guidance algorithm have been developed and coded and used in the onboard computers. Well, I think these developments were feasible. The hardware as well as software we developed, but it was not without encountering problems. If we take the first flight of PSLV, it ended up in a failure. There, all the rocket system, all the control system, and everything performed as designed, but still the mission did not succeed. Finally, it traced to a small software glitch which has occurred in the computer, onboard computer, and that has led to such a catastrophe. So this was a heartbreaking event. But then immediately we swung into action. We have introduced all techniques related to software configuration control, code walkthrough, code simulation. Then afterwards, hardware and loop simulation. That means the computers and control system, everything will be connected together. And virtual flights can be done in the ground itself. So such a system was perfected. And before the second flight of PSLV, we did something like 1,500 simulations, making variables in trajectory, in the disturbance which is encountered in the flight, and so on. With that confidence, we left to the launch pad, and that mission was a textbook decision, I would say. Finally, the altitude achieved was within something like 10 kilometers, and the velocity achieved was 0.1 meter per second out of 7.3 kilometer per second. So that kind of precision we could achieve using this one. And touch wood, so far, that type of system what we have used has not failed. So this is on the launch vehicle side, this is what we do. But when it comes to a spacecraft, again the problems are very complex. The spacecraft is put it into an orbit and just goes around here on and on. So they starts with the power generation. The solar power is the only main source available most of the time. So when it is exposed to sun, we collect this using here large solar panels, and then it is used in storage devices, batteries, and then used for the dark period, and so on. This, of course, in the small satellites, the power requirement will be about a kilowatt or so. But when it comes to the huge communication satellites we're operating today, we handle something like 20 to 30 kilowatts of power on board within a small space. Associated problems of power generation handling and all comes in. But more complex than that is what is called the maintenance of the spacecraft in orbit. First of all, if it is a low Earth orbit, it is continuously varying. Within 1.5 hours, it takes a complete rotation of the Earth. It has to be, its axis has to be pointed towards the ground so that we can make a precise Earth observation and so on. Similarly, the geostationary orbit, 36,000 kilometers above, the spacecraft to be stabilized. Again, its antenna has to be precisely pointed to the ground. So, very active control systems are required for this. Of course, we use small reaction control rockets for this purpose, for large disturbances. When it comes to small disturbances, what is called a reaction wheel is being used. A spinning wheel, and once its speed is varied, you get an acceleration in the lateral direction. And that is the principle which we is using. Continuously spinning wheels are put on board for this purpose. Again, for implementing all these, the rate measurement, the attitude measurements, and then converting to the commands and so on, that is done digitally. The sensors, a host of new sensors are required. When we had the first Earth observation satellite, we used a conventional television camera on board. So the result was from 600 kilometers, we could observe the Earth with something like 1 kilometer resolution, which is too poor. But from there, we started developing our own optics. There's a huge telescope, maybe about 600 millimeter to 1 meter diameter, and then the multi-layer charge coupled devices with a very fine resolution, like 1 micron technology we use. And these sensors pick up the images. And today we can proudly say that a sub-meter class object on the ground can be detected using this. Of course, these kind of sensors are useful only in the visible or the infrared region. But when it comes to the cloud-covered days, there is no other option go for radar techniques. Synthetic aperture radars are built and they are validated in the system, and that is being used for the radar imaging satellite for the night all-weather night vision type of missions. When you come to the communication satellites, the transponders which are required for this becomes a very critical element. These transponders are nothing but they receive the data from the ground station, then bend it back and send back to the desired point. So these type of transponders, initially we were working at a very low frequency region, like S band, C band, and so on. That means around 3 gigahertz or about 6 gigahertz and so on. But today you see the DTH transmission that is taking in KU band, which is around 12 to 13 gigahertz. And of course, now the KA band for the large bandwidth transmission is about 24 to 30 gigahertz. So various devices, transmitters, encoders associated with this is a big challenge. Of course, the basic device technology we are lagging behind, but we are quite good in systems engineering, and we have all our satellites are equipped with our own homegrown technology. Then comes for example, moon. When we went, we had to have a detailed mapping of the surface. There, the laser technique has to be used. Laser imaging technique using Doppler from the reflected rays, and then continuously mapping the surface of the moon. We could generate digital maps of the ups and downs on the lunar surface using this technique. So if you look at it, a wide spectrum of avionics components are being utilized, systems are being utilized, and they are put to the use in the rockets and satellites. Here, the strength of the Indian Space Research Organization initially started with systems engineering. Again, we have set a goal of achieving self-reliance in this field. In several fields, we have succeeded, but in some areas, like basic semiconductor devices, the infrastructure in the country is not yet come to the mark. We may have to put in additional efforts to revamp those facilities. Then we don't have to depend on anybody else for the avionics which is required for them. Spin-off of this is severally for the missile program and for the aviation industry. The navigation system, guidance and computer, the guidance and control system, what we are having, digital autopilot, all these are adaptable for the aircrafts. In fact, our LC aircraft use the spin-off technology from defense for these purposes. So that way, India can be proud that we have made a fairly good impact in all these areas. But we have a lot of challenges in the coming days. You must have seen the laser-based bomb guidance system which is used in the fighter aircraft. It goes to the extent even using a virtual reality, having a set of goggles, and the pilot looks at the target From there, it picks up the guidance signals and directs the bomb to the target and so on. So host of new technologies for imaging, data processing, and communication, all these are awaiting the future challenges of the new generation. Well, I think I don't want to extend my preliminary talk so much. Now I am prepared to take up some questions. Thank you.
Thank you, sir. Thank you for your kind input. There are a lot of questions in the question and answer chat box. So just very few we could take. Sir, like, can you tell something about Aditya mission? By the initiative has been taken by Government of India, ISRO.
Well, I think the whole existence of the planet Earth, is dependent on the sun. Its creatures, its various plants, and so on. So, to have a deeper understanding of the moon, initially a mission was conceived. Of course, it was a fairly simple mission, I would say. At the time, a spacecraft will be put into Earth orbit. Simultaneously, it looking at the solar phenomena like solar flares take place and so on. At the time, what effects it produces on the magnetic field and then on the terrestrial surface. So those are was the plan. But now that has been recast to look at the sun at a closer distance. The spacecraft is designed with very powerful telescopes, so it can look at the disk of the sun itself closely, and at a Lagrangian point, the spacecraft will place. So continuously, the observation is possible. We can get advanced warning about the what we call the solar flares and disturbances which can cause on the ground. And this right now in the design stage, sorry, in the next couple of years, it is going to be a reality.
Okay. So there is another question. Can you brief something about Gaganyaan mission?
Well, India has achieved all it can in the spacecraft technology as well as the rocket technology. So naturally, what is the next step? So human presence in the space is a logical one. In fact, I remember in 2009 itself, we have initiated this activity. At the time, government was willing to fund it, and we almost got it launched. But due to various political reasons, it was shelved and put in cold storage. Now I'm happy Modi ji has revived that. So the whole objective is we will design a capsule which can be carried the GSLV Mark III. It can have about a capacity for 3 passengers and a life support system for about a week. This capsule from outside looks so simple, but it is very, very, very complex one. This environment where we're living is microgravity environment. And again, the food waste management all become difficult. Hard vacuum in that itself to create an ambience where the humans can breathe and sustain. So these are big challenges. Again, the radiation from outer space is very heavy and has to be shielded and so on. But okay, it's one thing to send the people up, but we have the responsibility to bring them back safely. So that is a big technology by itself. When the capsule re-enters, you have all type of thermal problems and other thing. And there are in some missions, then the capsule has burnt off. Why? The space shuttle itself had such an accident. So to have a reliable launch system and to have a safe landing back, that's the kind of objective you have set for the Gaganyaan. And of course, the ISRO was entirely geared up for this, and they want to do in 2022. But unfortunately, this COVID period has derailed the program to some extent. But still, we will achieve that soon.
Okay. There is one question, sir. What is the technology behind reusable rockets?
Well, today, most of the satellite launches we are using expendable rockets. I mean, the rocket stage burns, and afterwards, the entire hardware with the rocket engine falls in the sea. And that way, the cost of the launch goes up. But at the same time, if the rocket hardware can be recovered and you refuel them and use it for the next flight, 10 times if you use, you know that 1/10 the cost only gets accounted per mission. So that way the cost of the launch can be brought down. Recently, the SpaceX have succeeded in demonstrating such a system, and it's a world-class achievement, I would say. But at the same time, in spite of all those recovery, etc., they are to be paid something like $11,000 per kg for access to space. Whereas the similar capacity, our GSLV Mark III can give about $6,000 per kg. So
Okay.
even without reusability, we are at it. But reusability will be something touching something like $2,000 per kg.
So expensive.
But you know, to bring back the used rocket, it will be traveling with a speed of about a few kilometers per second. So the velocity has to be killed. Then afterwards, when it re-enters the atmosphere, we should have a structure almost like an aircraft, wings and control systems and so on. And it has been slowly brought back to the site and made to land like an aircraft. We have in ISRO done a demonstrator flight of this, a small scale demonstrator which we put in a rocket and we went up to a Mach number of nearly 6 and brought back. So that's a small beginning, but we had to go a long way before we can be competing with SpaceX.
Uh, Sir, there is one more question. Is it possible to make all the parts of space rocket in India rather than buying parts from different countries? It will be cheaper and relevant for us also.
Certainly, in fact, I gave the example of GSLV Mark III. We are the most cost-effective launch system in the world today, mainly because for the rocket technology, about 80% of the items are built in the country, whether it is a materials, which chemicals goes with that, the control system or electronics or whatever it is. But some of the electronic components which is required, the integrated circuits or the microwave transistors and so on, that we have to still get from outside. So that costs about 10% of the cost to go. But whereas in a spacecraft, something like 50 to 60% of the components are bought from outside because you require a high reliability component to work in the hard vacuum and radiation environment. So that I think we don't have a base yet.
Okay. Uh, Sir, like one question, the mission Pragyayan. What is this Pragyan mission, sir? Any idea? Is it the mission launched by government? Pragyayan. Uh,
I'm not able to place it actually.
okay. Okay, no.
You
Sir,
have some brief idea about what it is about, I can guess.
maybe some miss question, I think so. Okay, so sir, another question we have: can we make our own space station? It will be the great help for managing our defense and communications.
Well, the next step of the Gaganyaan will be a space station. It is feasible. We can also send up modules, about 2 or 3 modules using the GSLV Mark III, put them together, and we can create a living condition for longer duration. There's no problem.
Sir, like in general question, like ISRO is in competition with maybe you can say SpaceX or NASA.
Well, we are not in competition with anybody. We set our own goals, our own priorities. Our main theme is meet the national needs. We make an assessment of what the nation needs. Something like a 10-year profile is drawn, and we try to accomplish those profiles in a systematic manner. In fact, that's the sole reason that ISRO is able to show results.
Okay. Another question is, sir, that recently Honorable Prime Minister has launched Atmanirbhar Bharat. So in that, ISRO has taken the initiative for in space. The various private firms are coming together and they are showing their interest in the startups. So what is your opinion in that, and what may be the career prospects for the avionics engineering or any other kind of the engineering?
Well, it certainly is a welcome move. Basically, the space commerce have got 2 components. One is the launcher, then another is about the satellite, and third component will be application. Once you have a spacecraft, you can use Earth observation for infrastructure management, communication. Of course, how the connectivity is provided for remote areas and so on, computer to computer connectivity. So these applications constitute nearly 80% of the market. That is where the potential lies for the startups. If they concentrate on those areas, certainly there is a lot of money involved, and they can show results in the coming days. But unfortunately, in India, all this program normally needs a fairly good investment, and return on investment is fairly low. All over the world, it is in a single digit only. No industrialist will be happy with that kind of returns. And also gestation period will be about a few years. So that is where really a mismatch exists. But government said that we will not put any blocks in front of you. You are free to take on the challenges of the space program and propose whatever the industry in the first can done. For the youngsters who are coming out of the college and see, of course, one is in the avionics area and all, there is quite a possibility of commercial production of the technology which is made by ISRO, and it can be used not only for the ISRO program but for many other applications as well. Then, secondly, I think they can take on this application program, whether it is in the communication. See, for example, even today, most of the communication equipment which is at the ground, they are being imported. There is a lot of indigenization possibility there. Similarly, the navigation, we have got the IRNS, that's the Indian Navigation System, it's already operational. You can use that to provide services which is better than GPS for various applications. So these are the niche areas one can concentrate, the startups can concentrate.
Sir, one very interesting question. Is it true that NASA research on aliens by caught them and without knowing others? Do ISRO also do research in aliens finding?
No, ISRO, everything is transparent. I don't think we do anything under the carpet. In fact, this is the only organization which is open to that extent. Then the second thing is, no, we are not in the business of looking for aliens, etc. But we join hands with some of the foreign countries in looking for extraterrestrial intelligence. See, there is a belief if there is some intelligence civilization, some part of the universe, they also may be conversant with the electromagnetic spectrum and its use for communication. If they send some communication, we can pick up that, and from there we can try to disable and so on. Huge antenna network is being set up in USA and some European parts also. And we participate in those programs to analyze the data and so on. But to my knowledge, so far, no such sensible signal has been spotted. NASA, they know pretty rather sort of guesswork, I would say. They have spotted at least 100 planets which are almost Earth-like in terms of temperature, atmospheric condition, and terrain and so on, which can support life. But the nearest one is about 4.5 light years away. So, you cannot, even if you travel at the speed of light, you are going to reach after 4.5 years. But today we are not reached even 1/1000 of speed of a light, our travel. So we had to wait before we can confirm these things.
Okay. Sir, actually, we have a very limited time and we have a lot of questions. So all the questions I will be answering on the later stage, maybe after combining. So thank you, sir. Just I would like to give the last word of thanks. Finally, on behalf of UPES Dehradun and the entire support staff and our esteemed attendees in the webinar, I would like to take this opportunity to place on record our heartily thanks to Padma Vibhshan Dr. G.Madhavan Nair for the gracious presence and taking out the valuable time of his busy schedule to enlighten us today. It's always our pleasure to have you, sir, and we look forward to see you again in the upcoming events also. Thank you so much to all the participants who have joined together. Thank you, sir. Thank you once again for accepting our invitation and delivering a fantastic talk on the topic rocket technology and the future scope of avionics engineering. Thanks a lot, sir. Thank you.
Thank you very much. I really enjoyed
Thank you,
talking
sir.
to the new generation and sharing some of the questions. If you find some important questions to be answered, you can mail to me. I shall try to do justice to the extent possible.
Sure. Thank you, sir. Thank you so much. Thank you.